right, hey y'all, welcome to my talk. I'm going to talk about basically validating metaprotocols on Bitcoin with script with governance basically, and we'll get into sort of like some of these definitions a little bit as we go along here, right? So first, what's the metaprotocol? What's some of like sort of like the validation paradigms in terms of like if something is actually known explicitly within Bitcoin, how are clients actually understanding what the protocol is and arriving in some sort of a consensus state? We'll get into the one I work on, Taproot Assets Protocol. Which we'll talk about Merkle tree validation. It's all about Merkle trees, as we're seeing throughout this conference here. Like if you don't know about Merkle trees, definitely get up on it. We'll talk about like a sort of a special Merkle tree that is used in Taproot Assets in order to validate the asset amounts, fairly easily. And we'll talk about some, how you actually validate sort of like how the asset exists, or even sort of like any state transitions within that. Then we'll talk about this, application something called Pocket Universe, which sort of simulates like a commit chain. People know those constructs, elsewhere on, some other chains. So first, what's a metaprotocol? So this is like a very abstract definition. Basically, sort of protocol that embeds some external data within Bitcoin itself for external validation, right? But the key thing is that Bitcoin is actually unaware of the protocol rules, right? For example, like you're putting some data in the chain, maybe it's explicit or explicit, but Bitcoin doesn't actually know what's going on, right? So some protocol maybe embed the data as maybe as far like an op return, or maybe some like very multi-sig outputs, or maybe others actually just embed a single hash in there and actually have like a much lower profile within the chain itself, right? So there's like a long history of these various protocols. People will hear recognize the self-color coins, Mastercoin, our counterparty, RGB, Taproot Assets, ordinals, inscriptions, runes. I would basically put all of these under the umbrella of metaprotocols, right? And on this list, most of them are actually variants that actually sort of like embed something explicitly within the chain, which I think has some other trade-offs. We'll talk about that, how that impacts validation, a little bit later on, right? That's a little bit of, I should have had that removed. But so the thing is, like, if your protocol, if your wallet doesn't actually understand how the protocol is, the question is like, how does it work, right? You basically need some sort of like, cohort to basically come to some sort of like consensus state validation to basically say, okay, like how do things actually work today? Like, so I think it's sort of like, two broad categories that people are actually operating this thing. One is basically indexers, right? So for example, the protocols that actually embed data explicitly into the chain, you basically need an indexer to sort of like walk through every single transaction in the blockchain itself, scan those for basically if it's a metaprotocol tag, maybe it's an op return, maybe some other identifier basically, and then, maintain that to arrive at the actual state, right? So number one, this requires an entire full node. So basically you have like the, half terabyte plus, state within that itself. And then you also have potentially additional state for the metaprotocol index itself, right? And if the protocol is like, doing some very like, direct ordering of all the Bitcoin and the chain itself, that can be very, very large, right? The other thing is that it's also not very like client friendly, right? Because you basically require the full node and then also this other thing as well too. And then you basically have, potentially hundreds of gigabytes. So you at least have half terabyte, maybe even approaching a terabyte of data with that. So, it's actually, very, heavyweight, right? And I think this sort of like, leads to many of them using sort of like, web collateral or maybe like actually very custodial heavy, because like if it's actually hard to verify that what you have is real, then people are going to skip that basically and just say, okay, well, that's probably real. I'll just, try to like flip it or something like that instead, right? Then we have the paradigm, called client-side validation. I think some people call this embedded consensus in the past. So basically this is like a different version where you're basically just validating everything that actually matters to you, right? So you don't really care about anything else going on. You're just saying, okay, well, if I'm accepting something or I'm like, interacting with something itself, I should validate that thing is actually correct. And this allows me to basically not actually, validate every single thing within the chain itself. And this is nice because now it's sort of like an explicit proof between participants basically, versus needing to scan every single item in the chain, right? And the cool thing about this is that you can actually utilize Merkle proofs in this construct, right? Because you only need a language, basically all the block headers itself. Ideally, if all the proofs are basically based into a Merkle proof itself, you don't actually need the full chain. You can actually use something on your phone, which is really cool, right? Yeah, and so it's nice because of the light clients, right? But now we'll talk about Taproot Assets for a little bit, right? So what is Taproot Assets Protocol? Basically sort of like a proof-based, bearer asset issuers transfer system built on top of Bitcoin itself, right? So what I mean by this is basically like the assets themselves are actually like a series of proofs basically. In order to verify a proof, you basically need to start the Genesis block, similar to the Genesis asset. So it's basically the way Bitcoin works. You basically have a Genesis block, right? Bitcoin is basically defined by the Genesis block, and then you walk forward from there. Any other chain that has just different Genesis blocks, for example, you have like Redtest, Simnet, all the other derivatives, earlier on from Bitcoin itself, those have different Genesis blocks. So basically, therefore, those aren't actually Bitcoin, right? And then you basically start at that sort of like Genesis asset, and you walk forward for every single state transition to basically make sure that something has actually been followed all the proofs. Then you arrive at some split output on the other side itself, right? You have a certain state transition function looks something like this. You basically have the previous asset, the asset witness, and then you have the new asset, and then you can go from there, right? And so one important thing I think for these protocols, like in my opinion, basically you need to have sort of like unique asset IDs, right? Because if you can't uniquely identify something, that's a big difficulty, because then things aren't necessarily canonical, right? I also think it's a mistake to actually try to make the names unique, because if you make names unique, then you basically have like squatting, right? You basically have someone that's squatting Google or something like that, and then that's not fun for anybody, right? So use something derived from BIP34, which is basically some software work that happened in the past, to basically ensure that all coin-based addresses or outputs are actually unique, right? And this is also something that also avoids sort of like having like duplicate transaction IDs in the index, which is otherwise assumed to be unique, right? So we have the Genesis out point, which is basically the first out point in the transaction actually creating this thing itself. Then you have the tag, which is the name, some metadata, the output index basically, and then also the asset type, and there's like collectibles or like normal assets itself, right? And that's how it is. So this is cool because now we can actually use sort of like the TXID and outpoint structure structure of Bitcoin, because you can say like, out points never repeat in Bitcoin, to actually generate globally unique asset IDs within the chain, which is a really cool property, right? And as you see later, this is important because we're going to actually be inserting this asset ID key into into particular trees basically, and these are like tries, and these must have unique keys within it itself. And this is really cool because it's basically like client friendly, right? As we show a little bit later, there's sort of like a series of proofs that you can actually obtain as a normal user, and the way it works as well, like we actually have this commitment that's actually going to be embedded into the tapscript tree as we'll see later, right? And because of this, things are very like like client friendly, right? Because you only just need a certain transaction, and then the proof you can basically verify receives some Merkle tree openings within that itself. And the nice part about this, like everything's based on Taproot outputs, for example, the channels and even the actual transaction itself. So everything basically just looks normal, right? You can't necessarily like pick something out unless you have the just metadata, along with it itself. And so that's really nice because now there's no sort of like preferential treatment for this unless you basically know, what it is about the protocol itself. But there's nothing within the protocol that actually gives away exactly what it is itself, right? And I mentioned a little bit earlier, so this thing has like a VM. Initially, it's basically just the TapScript VM. In the future, we can actually swap this out to be other VMs. Maybe it's like WASM or maybe something ZK based. But it's actually just actually based on Bitcoin all the way down. And a little bit later, that makes it a little bit easier to actually do validation of the protocol itself. Another important thing, which we'll see a little bit later, is that like the assets are actually built into a tree, right? The leaves in the asset actually have like an amount, and then you're going to sum those up to basically create like a Merkle sum tree, which is really nice because now the top level balance is the sum of all the assets, right? Which makes it very easy to sort of like, quote unquote, run the numbers within the system, which is cool because I can basically prove that, okay, well, if you gave me some asset basically, well, the output value should now be one less than what it was before, maybe if each asset has like a value of 1. And you can do a bunch of other additional things in it because like these are basically just Bitcoin transactions. You can do PSBTs, you can do normal swaps, you can do exclusion proofs, you can do a bunch of really cool stuff on top of it because it's Bitcoin friendly. And I was saying like we love Merkle trees here. Bitcoin developers basically have a bunch of trees, and this is sort of like the anatomy of like how an asset lives in a transaction. Right? First you have like the top level Bitcoin header itself. Then obviously you have transactions. Within that transaction you have a script, and that script is a Taproot script. Within that script you have a tapscript root, which has some additional leaves, and then there's like a special leave basically all the way to the right, which is like the Taproot Assets root. And then within that you're basically committing to several assets as well too, right? And then finally, all the way at the bottom, you have the asset TLP, which has a witness that also points to a previous asset, right? So that looks like very much Bitcoin-like at the very bottom there. And the cool thing about this is that, like, because we're committing to a tree, you can actually have sort of like an unbounded number of assets. Obviously, like, I think the actual practical limit is like 2 to the 128, minus 1, I guess, if you have, something on the side there as well too. But you can basically have a sort of effectively infinite number of assets in a single transaction, which is really cool because now you can have one transaction that like does end actions basically. Either that's issuance or maybe that's transfer or other things as well too. And we have that Merkle stone property, which means that I can easily validate that you have blah of some particular asset without maybe you necessarily revealing the root, and you can do additional proofs and things like that later. Succinct proofs, right? So one issue with this paradigm in general, and this is something that's been very much covered in the past, is basically state growth, right? Because like every single time we're making a new asset, we actually point to the prior one, prove the existence of the prior one itself. If you have something just simpler, like something that can actually never be, split, basically like a collectible, you have sort of like linear, growth on that collectible itself, right? Which means every single time you do a transfer, something that's very, very popular, you will have like, large state potentially, right? So maybe it starts out, manageable to a few kilobytes, maybe gigabytes, once you get to the gigabytes and terabytes, at that point, then it's sort of like impractical, and maybe even at that point, like, your thing maybe isn't as good as another individual's because maybe they have like a smaller proof with it itself, right? And, once you add, normal assets, basically, you can have like change and splits and things like that, because then you also have several inputs, and those inputs also have their own proofs as well too. You have quite a blow up as things start to progress more and more, right? But succinct proofs is a rescue, right? This is something that people talk about like a very long time ago. 10 years ago was considered math back then, but I think now it's actually pretty practical, in terms of like what you can actually offer today. For example, you can actually do recursive transparency proofs. People call them Starks, and and these are now possible. And the field is still accelerating, pretty quickly. Every few weeks or even a month, we basically have some new proof system, right? And here are some of the ones that are popular these days. Starkware has Cairo and Stone and Stew. Something called Risk Zero, which I think was featured in an earlier talk. We have SB1, another additional one, and then something called Jolt that's usually a little bit different proof system itself, right? And it actually addresses a number of the design constraints within these client-side protocols, right? Because now you basically have the reduced to a single blob, right? Rather than like a proof that's always like pending, sort of like a blockchain or linked list, basically, you have one proof, and then if you want to do something new, you basically sort of like compress the proof that like the prior instance was valid with the proof that this new instance is valid into a single proof. It almost looks like sort of like a hash function, construction basically there. This is also cool because now like proof can actually operate over the entire constant of a block, meaning that you can do things like prove, the ordering within transactions. You can prove the output value. You can prove that like something else was in that block itself. And the cool thing is that like assuming that you have you yourself have like the block headers themselves, like the proof would actually also be doing things like proving POW, proving header correctness, proving the validity of the block headers as well too. And you have that one proof. Maybe it's gonna be like 100 to 200 kilobytes or so, but it's still better than it being bytes or gigabytes, which is very, very cool. And here's like a sort of like a sketch of how something like with this like that within the Taproot assets itself, right? So you basically have the sort of like state transition function I mentioned before, previous asset, new asset, witness, and then you basically have another additional thing that basically takes the previous Taproot and sort of like witness data, and then gives you a new Taproot thing itself, right? And there's sort of like two layers, right? First, you're going to prove inclusion. You say, okay, well, there's a valid block header in this chain itself that has valid POW and follows all the rules, difficulty estimate, whatever else, or I mean that's like within that context itself. Then it also says, okay, well, that commits to a transaction that has a valid Taproot output with a tapscript root that has a leaf which has these attributes that have such and such properties with itself, right? Then you also have state transaction validity. You're saying, okay, well, based on that instance, basically I proved inclusion to this block itself. Now I also prove that like this state transition is actually valid. So it's okay, well, based on these public inputs, which are actually maybe some in the blockchain, some actually provided as part of the proof, we actually prove these things that now follow the rule set contained in YYY itself. Then you actually recurse. Then you say, okay, well, each of these inputs also has a valid inclusion of the state transition proof itself, right? So now you're basically composing all these proofs together to the form where you basically just have like one single proof. And then also now this is really cool because proof is basically the state or the asset itself, right? Now you're actually pretty desynchronized from the entire system, which is a very cool property. Yeah, and then each basically feeds into the prior layer, with the new layer for recursion. But now we're getting to sort of like some of the meat of the talk. Basically, okay, like how do we actually validate something like this within Bitcoin script? What it actually looks like, and also maybe what are some of the benefits of doing so in the first place? First, we have like the initial first proof layer, which is sort of like the block header Merkle proof validation, right? So you have like this 80 byte block header itself. It has the Merkle root within that itself, and then we know all the transactions are basically hashed into a single Merkle root, which is easy because they can do that directly there. And opcat to the rescue in this instance, right? Because we can basically just use opcat. Use sort of like an op dupe SHA-256 opcat again to basically then incrementally construct what this root is going to be itself, right? So obviously we need to do additional functionality, basically validate that the block header is actually valid. You need to do some PAL stuff, things like that itself. But the inner thing, as far as like being able to concatenate and hash two items, basically Merkle tree validation, we have that itself there. But one kind of a quirk with this is that like with the way Merkle trees work, like this script is actually dependent on the number of leaves and the height of the tree itself. For example, are you going to be hashing 8 times or 3 times or 5 times or 10 times, right? So therefore, you need to unroll all of these values basically into the tapscript tree, which can be kind of large, but maybe if you're operating off of fixed size Merkle trees, which is a little bit later, it can be a little bit easier, right? But then you basically unroll all of these elements and then actually pick, based on what the condition is, basically which validation script you're going to be using within that itself, right? But then, within Taproot Assets, we actually use something slightly different. We basically use something called a Merkle sum sparse Merkle tree, right? And sparse Merkle tree is similar to Merkle trees. It's actually which is something called a tree. People know about it basically, and the difference between this and like the other Merkle trees is that like the height of it is always 256, right? It's always a fixed height tree, right? And you can say, okay, well, obviously that's massive. That's like a bunch of hashes. Like there's no way it's going to fit in RAM or anything like that. But the thing is, like we can actually sort of like simulate this Merkle tree based off sort of like this empty hash construction, right? So we basically start with the root value. We can then hash that, to arrive at the left and right values, and then continue on and so forth, right? So therefore, at every single level, we basically know what the empty hash already is. So an empty tree, isn't something with 256 256 leaves is basically just a single hash, which is the top level empty hash value, right? So you can sort of like simulate this value to actually make it a lot more succinct, basically. And the interesting thing with this one is that you actually don't need to unroll the validation loop, right? Because it's always going to do 256 hashes no matter what, right? So you can say maybe there's some trade-off there as far as like size, but I think it simplifies the protocol a little bit because you can actually ensure you're always hashing the exact same amount of times. You don't need to unroll anything within it itself. And to the right, you basically see sort of like how we construct this empty hash map, basically. You basically have a map of the height of the tree to basically what the empty hash value is, and you can go all the way down. And now using this, you can basically look up something into the index or the height of a tree, basically, and then see exactly what level that thing is at, right? And then Taproot Assets basically goes another layer and basically adds a sum layer, right? So in addition to like this number hashing structure, you're also going to be summing the values in each of the leaves as you go up all the way, which is cool because now you can basically have a single value that's actually the total sum of the supply, basically, right? For example, we have something called a universal issuance tree where you're going to basically insert proofs of like the existence of all these assets, and then the top level value is going to be the sum of all the assets itself. So basically, this makes it easier to do things like quote-unquote run numbers, sort of like a built-in sort of like proof reserves type system. And then this is like some ways this is like on the right here, sort of like how the structure works, where you're basically hashing these two, or you're summing the two values and then putting that into the digest itself, and it's based on like if you're branch or a leaf. And one other thing, because it's like a trie, the way you do the lookup is that like, you're actually going to be looking at the individual bit on every single one of the keys, right? So each of the keys are 256 a bit, right? And you're going to be looking at the initial index to decide if you're going to go left or right. So if the bit is 0, you go left. If it's right, if it's a 1, you basically go right. And they basically use this to basically go all down on the tree. And this is the thing because you can view it as sort of like every single element has a unique placed within the tree itself, which is really cool. And this basically means things like it's canonical, it's history dependent, and also, it also makes it easy to do things like non-inclusion proofs, basically. So for example, with a Merkle tree, typically you need to like have all of these be sorted in order to do non-inclusion proof. It's okay, well, it should be here, but it's not here, and these two siblings are here on the right side. But for this one, doing a non-inclusion proof basically shows that it's actually an empty hash, which is something a little bit more straightforward and useful for these protocols. But for example, like if you're giving me something in this protocol, I want you to prove to me that you're no longer committing to it, and you can do so easily with this non-inclusion proof. But the difference is, like, doing the SMT adds some additional new challenges as well, because, for example, like, if we go back to the slide, you see we're actually needing to branch on the bit condition, basically, right? Versus a Merkle tree where it's like, sort of like just hashing, and it's a little bit simpler thing. So therefore, you basically need an ability to do some additional sort of like, bitwise arithmetic, right? And some, as we know, many things in, Bitcoin scripted are disabled, and you need sort of like a routine that looks something like this, can probably optimize a little bit further, so that maybe you might need some things like, some of the shifting opcodes, maybe potentially partly the great script revival itself, right? One thing that maybe you can do, you can potentially even try to like split up the elements into like individual bytes on the stack. So basically, don't put the key all at once, basically, and then split it up instead. And maybe you can do some simpler manipulation with that, or maybe just do it bitwise. If you just give me the entire key as 256 bits, obviously I can just do the normal operations. I can compare them, versus doing anything beyond that, which is really nice. One other thing, you basically need, arithmetic, right? You need basically, if we're going to be having, 32-bit elements within the value tree, maybe you also need 64-bit arithmetic or beyond, basically, in order to actually represent these things, in an easy manner. And I think some people showed before, maybe you can also implement the stuff with bitwise decomposition, actually just do your own add, but maybe that would be like somewhat of a larger operation within the tree itself, right? So now that we have all that, we can say, okay, well, how do we actually validate, asset? So first, we can use opcat to construct the serialized, TLV leaf, which is basically some attributes. For example, this is the asset ID, the amount, the metadata, the script key, and other information like that. We're on the script key layer. Then you're going to actually hash that into basically the SMT root to derive this like top level script, which is actually then committed to within tapscript, tree. Then you're going to do another hashing layer, beyond that to actually get the tweak that's actually going to be part of the Taproot output, basically. And now at that point, you have like what should be a valid Taproot output, then you can actually continue on the way up and actually do Merkle header validation within the script itself. But we do need a final layer. We basically need some sort of like opt to verify, basically effectively what something like opt check contract verify opt CCV does itself. Because once you have that tweak, you need to be able to actually verify that the output matches that value, right? Basically, and this is sort of the existence. Alternatively, you could break it down to like components, basically like something like opt EC add, EC mul, and opt internal key, basically to be able to verify the two components. But you need something like that itself, right? But then once you're able to verify that, you can then verify, okay, well, because I followed all these rules, there's a leaf in the tree, which is within another tree, and that has this value, which is adds to this particular public key. I verify that something that actually exists as an asset within this itself, which is pretty cool. So now, remember, like first we're doing two things. We're going to basically do inclusion and also state changes and verification itself. So we just covered inclusion. Inclusion is basically you have something in these, series of trees, you follow all the rules. Now we actually need to follow state changes and verification, right? For example, like in Bitcoin, you can't spend an output until you satisfy the script. In many cases, that's just like a single signature, basically, right? We need something similar to that. But Taproot Assets actually just uses Bitcoin script VM under the hood, which is really cool. So for example, we take sort of like this multi-input, multi-output structure. For example, like your asset is basically referencing a bunch of other inputs, which is sort of like a superset of a prevout. So in addition to basically the output, the TX hash and the index itself, you also then you need to give me the asset ID and the script key. So it's basically this for tuple to allow you basically uniquely navigate down this tree. And what we do, we basically do something called like virtual transaction, right? So basically we map that multi-input, multi-output structure into one single transaction. And this is like a something from the BIP basically shows how you like map those inputs into one single output. So what we do, we actually insert all of the inputs into another tree, which is also an SMT, and that sum is going to be the sum of all the inputs. Then we insert all the outputs into another tree, and now we can basically verify that nothing's been inflated because the two sum values should match up just like on Bitcoin, right? There's no explicit fees because fees are actually paid on the upper layer itself. Once we have that, we basically make something called like a fake virtual, a prevout basically, which is just the TX ID of the virtual transaction that we created here. And then similarly, we do something, similar for the TX outs. For example, like, collectibles can never be split, so you basically put that indirectly, but something that's normalized can actually be split. So we have something called a split commitment root, which is sort of like a commitment that includes the actual output, then also all the change output as well, too. Now we can verify these two things within itself. And the cool thing, once again, is that we have something called a script key, which is actually just a Taproot output public key, right? So therefore, using these tricks, you can actually verify that, like, in addition to everything being, included, basically, you can also verify state transition validation because you can use some of the opcat tricks to basically reconstruct the sig hash, of the virtual transaction itself, and then validate the signature that's included against that thing itself. Which is really cool because now we're able to verify, number one, that the thing actually exists, and also that that's been done correctly. So as I mentioned as well, like these are actually Taproot output public keys. So in theory, you can actually do script validation as well, but that's going to need some sort of like feedback thing because you need to validate the control block inclusion, which is Merkle trees. You can do that itself, but then validating that the script is actually valid basically requires you to basically recurse another layer. So for now, at least in this concept, we're going to be restricted just to key spend validation, right? And then so this one thing, I think is sort of the motivating factor of this one's like something we call Pocket Universe itself, right? So it's basically sort of like a commit chain type structure where every single block you're basically committing to some new state itself, and that state is sort of like this tree. And something called NoCust, which people maybe remember, this is from like 2017 or so basically, which is sort of like inspired by. The cool thing about this is because like all the user balances, you can say every single user is going to have like their own leaf within this tree itself. Because that's committed to at the top, you can verify sort of like that things are being done properly. For example, if no one left the tree, the sum value shouldn't change. If someone left the tree, the sum value should be different. If someone added more funds, the sum value should be different, and so forth, basically, right? The cool thing about this is that, like, because now we're able to validate the state transition and inclusion of these leaves itself, we can have a coordinator that basically controls that top-level Bitcoin output, but can't unilaterally spend it unless it follows the rules of this protocol itself, right? So, for example, it's going to commit to all the leaves, all the participants itself, and one thing is like because we also have signature validation for the state transition itself, they can't forge your signatures. They can't necessarily just steal the asset as well, too, right? And if we're able to actually restrict them a little bit further as far as like state transitions, if they need to prove basically like any single modification to the tree as far as giving the internal nodes and also the new leaf that's been modified itself, they can't also just like remove funds from it itself. This is cool because now you can sort of like compress the state, the chain footprint of the system into basically one input, one output that's actually moving into the chain every single time, right? For example, otherwise, let's say I had 100 users. The 100 users basically make 100 transactions, so it'd be 100 Bitcoin transactions itself. But in this case, we make 100 transactions in Pocket Universe just this in this one layer itself, which is very cool. As I mentioned, like now that we have script validation, the operator can't just like spin it up in an invalid manner, and it also can't necessarily move out from the tree itself. I think there's a number of really cool extensions. For example, you can actually open channels, which people saw in my tweet a little bit earlier. We did for the first Taproot Assets channel on mainnet. You can open channel within the construct with just at the Taproot Assets layer itself. You can also, like in theory, sort of like lift your Bitcoin output into the system itself by sort of spending your Bitcoin and then creating something that represents it in that system itself, and then putting it into this construct to maybe enjoy some of the scalability benefits. You can do things like atomic swaps, ACLCs between these Pocket Universes as well. I think it also composes well with things like ARC, channel factories, basically anything that sort of like has these multi-party off-chain contracts can also be done in this because this thing basically is a UTX. So it basically is a Taproot Bitcoin output itself, all the lowest layer, which I think has some really cool properties. That's talk. And if you think this stuff is cool, work on the Taproot Assets, Bitcoin, Lightning, ZK stuff, we're hiring. Thank you. There's a question over here. Yes, because like the commit chain itself is going to be committing to a tapscript root, and that root itself is committing to basically all of the asset or user balances within that root itself, right? So therefore, like we're spending that with basically one output on chain, but we can potentially have many different leaves that have been modified within the chain itself, right? But in theory, in order to like validate this properly within Bitcoin script, you basically need to provide sort of like the delta, which maybe is going to be a signature of a leaf that changed, right? So and this is going to go in the witness data. So it's going to be like it's not actually going to be make the bar transaction larger. We also get the witnesses discount that showed is a little bit cheaper. Yeah. Sure. Yeah. So everything I describe here basically assumes sort of like post governance because like it's kind of like the script thing. But I think the interesting thing is like if we go back to I got a lot of bullet points. 1 second. One more. This. If we go back to this layer, right, this can be built today, which is really interesting, right? So this is sort of like, so what I described is sort of like explicit, validation, basically. Well, this is sort of like more succinct validation, right? So assuming you can verify, for example, some people know ZeroSync, basically a protocol that sort of like, started a SPV proof on Bitcoin, basically. That required them to basically validate all of the headers, basically validate all of the Merkle trees, things like that within the system itself. So assuming you have that, and then if we go to this layer, so we've done everything from the top up basically, and then the bottom down. Then we're going to actually do the tapscript stuff there. So that's really cool in that like if we run into like sort of like sidestep this, we could just use some of these other succinct proof systems basically to write our program, our validation within the proof system itself, and then gain some of these benefits as well. And I think this is cool because like in theory like there's a sort of like version of the protocol, so you can actually make something that's a lot more sort of like snark friendly. For example, right now we use SHA-256. We can use other more hash friendly functions. We can use a different vector commitment that maybe also can have our some properties other than the Merkle tree as well. So I think it's cool because we have these sort of like parallel paradigms we can follow. And I think in terms of like order operations, I think we'll be pursuing this one first to basically start to actually create ZK proofs of these asset proofs as well, because that lets us address the scalability benefits. But I think then it would be cool to be able to validate some of these rules within Bitcoin, because if you can validate the rules within Bitcoin, you can make sure that someone can't spend an output in an invalid manner. Otherwise, because you can't validate all this other more fancy sort of like scripting on the higher level layer, someone can basically maybe violate the contract with no penalty, or they can even just burn coins. And today in the protocol, whenever like someone doesn't follow the rules, the coins are just burnt, right? But it'd be cool if you can actually validate that they're following the rules and they must follow the rules in order to spend the output. But otherwise, I think we'll be getting into some of these ZK stuff very soon, which I think is really exciting. Oh, and the cool thing about this is many of these systems now support sort of like a RISC-V compilation target, right? And much of our code is written into Go, and there's something called time to Go that can actually compile Go into RISC-V, right? So assuming those systems can basically be modified to like, match like the ELF format of some of these systems, basically, we can reuse all of our code to generate this, this proof on the system, which is very exciting. Yep. Yeah, so I gave another talk last year at the Starkware conference, basically, and I talked about sort of like that portion that, like, you mean like Lightning gossip, right? Yeah, exactly, right? So today, like, once again, like, everyone downloads all of the Lightning, proofs, basically. They do all the validation, they fetch the block, which can be actually take some time. I think that's also why people like LDK made, like, the rapid gossip sync, basically. But in theory, if someone could publish a single root, basically, of what was considered the gossip state, and then also that root as actually a proof that every single one of those outputs existed at some point, you can't really necessarily do unspendness because you don't have, like, a UTXO set. But someone could basically just download that single root, verify the proof, and then download the graph and say, okay, this stuff is actually valid, right? And this is like a step up because obviously you can just download the graph from somebody, but it could be completely hypothetical, it can be made up. This basically gives you additional sort of like trust anchor within that. So I think that's another really cool application. And I think that's cool because, many of these things can be done today in terms of like, proving out some of the tooling without necessarily modifying Bitcoin as is. And I think like people talk about putting like a ZK proof system with the Bitcoin, but I think still today, like it's moving very, very quickly. Like, I mean, so like every maybe 6 to 9 months, there's a new proof system basically. And it's okay, well, which one are we going to choose? Things need to settle down somewhat. It's not really, showing signs of slowing down. I think people are going I think we talked about people before basically doing something the ugly way and then basically having it be something a little more efficient. And people are actually working today on basically doing Stark verification with OpCat. There's something called Bitcoin Wildlife Project or Bitcoin Wildlife Sanctuary. That's really cool. That I think people will be very excited about soon. That's actually doing that very thing. So cool. Thanks.